Hello. I want to show how, through the use of Cartesian tensor notation, the equations of continuum mechanics can be considerably simplified and become very easy to remember, memorize, manipulate, and work with. The equations of continuum mechanics are generalizations of Newton's second law of motion, combined with expressions of constitutive behavior of materials. The first group of equations are the so-called momentum conservation equations or equation of motion. The equation of motion essentially is a restatement of mass times acceleration, and it indicates that the mass times acceleration on the left-hand side is equal to the sum of forces acting on the material points in the continuous body. The first three terms on the right-hand side involve doubly subscripted quantities called the stress tensor, and three partial derivatives are involved in each of the terms. Each term represents a component of the momentum equation. Since the force and acceleration are vectors, then we have three component equations of motion. The constitutive equations of material behavior are the representation of the response of the material to the load. Specifically, we know that to get more stretch out of a solid piece of material, we need to apply more force. This was known and stated by Hooke, and it's been generalized in terms of the stress and strain tensors, as indicated in there. Only 6 equations are involved, since both the stress and strain tensor are symmetric. But you can see on the left-hand side doubly subscripted stress tensor components, and on the right-hand side doubly subscripted strain tensor components. The elastic constants are the only two that are needed for the case of the linear elastic isotropic solid. When these two equations are combined together, we obtain what is called Navier's equation. Navier's equations are essentially the equations of motion, in which the terms involving the stress tensor have been replaced through Hooke's law. Two terms involve derivatives of displacement. Now, the key notational ingredients that we will need from Cartesian tensor and notation are, one, the index notation, through which instead of writing xyz for the Cartesian coordinates, we write x1, x2, x3. The unit vectors are therefore replaced as well by, instead of I, j, k, one writes e1, e2, e3. On top of that, one uses the so-called summation convention, and this is very simple. It just says that whenever the same subscript appears twice in any equation, what is meant is the summation over the range being 1, 2, and 3. Last, we'll use the comma notation to indicate partial differentiation. So with this, we can write down the index notation as indicated in there. We replace xyz, the coordinates, by x1, x2, x3, and the unit vectors by e1, e2, e3. We can then write the position vector as indicated in there. Instead of writing as indicated first here, we end up writing summation of terms, x1, e1, x2, e2, x3, e3. Then this is obviously a summation because of the use of indices. And through the use of the summation convention, we get rid completely of the summation sign, and the summation is implicitly understood whenever two subscripts appear in the same term. The displacement vector can be written down in the same manner, and the velocity vector likewise. More complex terms, such as the strain deformation gradient. The deformation gradient tensor is an entity consisting of 9 quantities, as indicated in there. Essentially, the partial derivatives of the various strain components with respect to the coordinate directions. Through the use of the comma notation, you can see that utmost simplification is obtained by introducing a comma between the two subscripts I and j, one obtains essentially the same significance as this whole collection of terms. The strain plays a very important role in all of this. The strain tensor is a combination of various derivatives of the displacement in various directions. Because of the way it is defined, the diagonal and off-diagonal terms are involved. Diagonal terms look very much the same, and the off-diagonal terms look also very much the same, except that the indices are different in all of them. When one uses the notation of Cartesian tensors, all this complexity is reduced to a very simple collection of two terms, which is indicated there as 1/2 partial of ui with respect to xj plus partial of uj with respect to xi. Through the use of comma notation, this can be further simplified even more to what is shown in there. And of course, one can use a single symbol to represent the strain tensor as indicated in there. But never forgetting that the strain tensor is defined in terms of these quantities there. The stress tensor is very similarly defined as indicated in there. Is a collection of 9 quantities, and through the use of index notation, it can be all those 9 quantities can be replaced by just one. When all of this is put together, we come to the end, in which we see that the equation of motion is very effectively reduced in complexity by a significant amount. Is written down just in terms of 3 terms. The term on the left-hand side is the acceleration. The first term on the right-hand side is the collection of partial derivatives of the stress tensor components, and the last term on the right-hand side is the body forces. The Hooke's law, the constitutive equation of behavior, is also, instead of 6 equations, one reduces this to one single equation. Obviously, by varying the indices from 1 to 3, one can transform this single equation into the 6 equations presented before. And last but not least, if these two things are combined together, one obtains Navier's equations, the acceleration on the left-hand side, and on the right-hand side, the second-order derivatives of displacements in the first 2 terms, and the body force, and again, a vector equation. Hopefully, through this exercise, I have been able to persuade you that it's possible to significantly reduce the complexity of the governing equations of continuum mechanics of the isotropic linear elastic solid, and producing something very simple, very easy to remember, and very easy to manipulate.